Now let's move on to a topic known as regularization techniques. We saw in previous examples that when we train the network, we want to train on the training set and test on the test set. And during this process, we want to monitor both the training error and the test error. If the training error is not decreasing, the network architecture might be unfit or insufficient capacity. The solution to this would be to add more layers, more neurons, or use a different network architecture. If the training error decreases, but the test error, which is in the green line, plateaus or increases, then we talk about overfitting. This means that the network might memorize the training set, but it fails to generalize to the test set. Take an example, a student that trained on the same examples in the class, then he got or she got high marks. Then when he or she tries different questions, unseen questions, then his or her mark fall down. So we here introduce the regularization techniques to address this overfitting problem. The purpose of these techniques are to reduce the gap between training and the test error. First, let's talk about early stopping. In some cases, both the training and test error will start decreasing to begin with, but when the test error starts to rise in the blue line, in such a case, we can use a technique known as early stopping. We will simply stop training at this point of the smallest test error. However, it can sometimes be hard to determine where this point is because the error might statistically rise and fall over each epoch. The solution here will be to periodically save the model weights, and once we've gotten to the point where we know where the minimum error was, we can reload that stored weights for that model. Another technique called weight decay. Another common regularization we can use, which called also L1 regularization and L2 regularization. This formula represents the L1 regularization. We modify the cross-entropy loss function by also adding a penalty term lambda. We will be multiplying the absolute value of the weights by a constant lambda. We add them together. And L2 regularization, we will use the squared weights rather than the absolute weights. Since the learning algorithm strives to minimize the loss, this penalty term will imply that it also will try to minimize the weights. This will result in decreasing weights that solve only some of the examples, because these weights will incur a penalty for all the examples, all other examples, but without much benefit. This is how weight decay will lead to better generalization. Number 3 of the techniques is dropout regularizations. Perhaps this is the most effective technique for neural network. Here we randomly drop neurons during training. We drop different neurons between each mini batch. According to the paper where this was introduced, this will force the units to work with random sets of units. As always, when training neural networks, it's not obvious which technique to use and when. You will simply have to experiment for different problems.